Hello, my dear. Welcome to IMS Gate Academy. I hope you are all good and your preparation going to be in the right direction. I am Pragyabrat Tripathi, Faculty Department of Mechanical Engineering. So, my dear, today onward, I will start a series of PYQ of thermodynamics, okay? And also there is application part. So, my dear, this session is useful for the mechanical engineering, chemical engineering also, and also one second beta, chemical engineering and also production engineering, food technology engineering, all this branch, agriculture engineering also there. So for this one, this session is important. Okay, so today we will discuss 2022 questions. Okay, what is that? The first question, see my dear, in the thermodynamics, there is a first law, and the first law there are three domain. First is the first law for the closed system. Second is the first law for the open system, in which there is a steady flow problem. Third one is the first law applied for the open system, but the system is unsteady. So this is your unsteady flow problem. Read the question very carefully, and in this question there is nothing is that, but the thought process, the approach are a very important. Okay, approaches are very important. What is that, beta? See this one. A rigid tank. What is the mean by rigid? That means volume is constant. Okay, of a volume 8 meter cube is being filled up with air. Air act as an ideal gas from a pipeline connected through a valve. Okay, initially the valve is closed and the tank is assumed to be completely evacuated. That means initially, that means when the valve is closed, at that time the tank is empty. That means the mass of the system at the state first is 0. The air pressure and the temperature inside the pipeline, that means the fluid is flowing with the pressure and temperature is 600 kilopascal and 306 Kelvin respectively. The filling the tank begins by the opening of valve. Okay, this is the process, and the process end when the tank is equal to the pipeline pressure. That means at what level you have to supply the air, at which the container pressure, that means a system pressure is equal to the pipeline pressure. That means pressure are equals. Okay, now during the filling process, heat losses. This is important thing. That means while you are filling the fluid inside the tank, the heat will lose. That means you cannot neglect the heat losses. Okay, so there must be a heat loss. Okay, and what amount the heat is losing? The heat is losing 1000 kilojoule. The specific heat, the property of the air, it is given at a constant pressure, it is given, and a constant volume it is given. You know this thing. Neglecting, this is very important, neglecting the change in kinetic and potential energy. That means the system is stationary. The system is stationary. Okay. Now, my dear, they are asking that the final temperature of the tank after the complete process. That means once the pressure is equalized inside the tank and the pipeline, that means the process is end. What is the final temperature of the tank? Okay. So, my dear, let's start. So first this, so we have to start this one. See this one. This is your supply line. Okay, that means charging. This is the example of charging. Charging and discharging is there. So this is the example of charging. That means flow of unsteady. That means why? Because the system, if you take, this is our system. That means there is a supply line. In the supply, the fluid is flowing. Okay. Now you open this valve. When you open this valve, the fluid fluid enters into the control volume. Why? Because the mass is in. So mass transfer, the system when involve the mass transfer, there must be open system. So mass is in. Now during the mass in, the system property will change. Okay, so in this one there is no any exit condition. So this is your, let's suppose this is our control volume, and when the valve is closed, the control volume property at point 1. Now at the end the process, the system property at point 2. So its property will change. Now this is our entry, that means this is our I, entry is there. So during this one there is a fluid is flowing. So in this one beta, you have to label 4 things. First is entry I, exit E. So let's suppose section I and E, state 1 and 2. Okay, state 1 and 2. Now my dear, thank you sir. Now my dear, thank you Atul sir. Now my dear, the section I. So this is your entry section, this is your exit section, this is your state point 1 and this is state point 2. Okay. Now my dear, there is no any exit. Why? Because this is your charging. So exit, what is the exit property? These are 0. Why? Because this is only charging. Now state 1 and state 2. Now my dear, initially the control volume is evacuated, that means there is no any mass. So initial mass, that means M1 initially, state 1 is equal to 0. Okay. Now what is the given here? Tank is rigid, that means V1 is equal to V2. That means initial state in the form of volume of the system is the final state in the form of volume. Okay. So V1 is equal to V2, it is given, and it is how much? 8 meter cube. Clear? Now what is given? Initial mass is 0. Now the inlet pressure, that means inside, if the supply line, in the supply line there is a Pi and Ti, it is given. The value it is given. Inlet pressure and temperature it is given. What is the inlet pressure? Pi. How much it is? How much it is given beta? It is given 600 kilopascal. In the question it is given 6 kilopascal. Only I am noting the given condition. And inlet condition temperature it is given how much? 306 Kelvin. Okay. Final state. So this is your inlet. No exit. So exit is 0. So this is your inlet condition. Now what is the state 1? Now the final state. In the question they are saying that the final state of the system is equal to the pressure in the supply line. So P2 is there. P2 is equal to Pi, and this is equal to 600 kilopascal. It is given. Okay. During that, heat will lose. That means heat will lose. This is your Q122. Heat will lose. That means heat losses by the system. That means Q122 is equal to minus. Why? Because it will lose 1000 kilojoule. Okay. Now Cp air property it is given. Cp is equal to 1.005 kilojoule per kg Kelvin. Specific volume it is given. Cv is equal to 0.718 kilojoule per kg Kelvin. Now my dear, in the question it says that change in kinetic and potential energy are negligible. That means in this question this says that delta Ke and delta Pe is equal to 0. The change is negligible. That means the system is stationary. That is called the system is stationary. Okay. Now, so we have to find What is the final temperature T2? So we have to find the final temperature T2 of the system. This you have to find. No, my dear. No, my dear. When you have to find the final temperature, in this question we have to apply the first law of thermodynamics, but for the unsteady state. So what is the first law of thermodynamics for the unsteady state? So what is the first law for thermodynamics for the unsteady state, beta? Please tell me, what is the first law for the unsteady state? First law for the unsteady state. First law for the unsteady state. First law for the unsteady state. Okay. So we have to apply first law of unsteady state. Unsteady state. Okay. Why? Because unsteady state. Why? Because the property will change. What is that, beta? What is the first law? Conservation of energy. That means we have to apply the conservation of energy for the unsteady. Why? Because charging and discharging of a tank is a kind of unsteady. So what is the first law? Please tell me for the unsteady state. Heat transfer Q. That means energy in minus energy out. See, what is the first law? What is the conservation of energy? Energy in minus energy exit is equal to change in energy of the system, E2 minus E1 of a system. Yes or not? Yes or not, beta? This is the conservation of energy. So in this form, energy in, it is in the form of heat Q plus the energy in and energy. This is the energy transfer. And this energy transfer is due to the mass, due to heat and due to the work. So in this process, there is no any work transfer. Charging or discharging, in this process, there is no any work transfer in this case. But there may be a heat transfer. So this is your energy transfer. Energy transfer. And this is your energy change. Energy change. Okay. So energy transfer, it is in the form of mass, heat and work. Okay. Mass, heat and work. In this process, there is no any work transfer. In this process, there is no any work transfer. Only mass transfer is there. So Q is in, mass in, and due to the mass in, there must be, due to the mass, there must be a specific property. That means the property of the fluid. What is that? Enthalpy in plus kinetic energy in by 2 plus GZI. This is your inlet. Now, what is the exit? If you take the exit in this side, so this is the exit condition. Now, so this is your in. It is in the form of energy in. E in. Okay. Now, we have to take equal to change in energy of a system. Change in energy of the system. What is the change in energy of the system? E2 minus E1. That means with the help of M2, there must be a U2 plus V2 square by 2 plus GZ2. Yes or not? Minus M1 U1 plus V1 square by 2 plus GZ1. So, my dear, this is your change in energy of the system. That means this is your delta E of system. Now, energy in is equal to delta E of the system plus energy exit plus energy. How to write this one? Energy in is equal to delta E of system plus energy exit. You can write like that. So energy in is equal to energy change of the system plus energy of the exit from the system. So plus, what is the exit? ME HE plus VE square by 2 plus GZE and plus work. This is in the form of shaft. So this is your exit energy. Energy exit. Energy exit. So this is the conservation of energy. That is the very simple thing. Now, my dear, so please write these things in a very proper manner. You have to, when you have to solve the Bernoulli equation problem, first you have to write the conservation of Bernoulli equation. Then you have to take the assumption which is the given condition, which is the given and which is not given. Accordingly, you have to take a 0. So once for the any equation, if apply the conservation of mass, conservation of momentum, conservation of energy, any type of energy, when you have to apply, first write full form of the equation. Then according to the question, what is the given, you have to just put the value. Now, my dear, first thing, it is given that change in kinetic energy and potential energy is 0. If the change in kinetic energy and potential energy of the system is 0, that means the system is stationary. So you have to take the change in kinetic energy and potential energy is 0. Then we have to take this one is 0, this one is 0, potential energy, this kinetic energy is 0, this potential energy is 0, this kinetic energy is 0, this potential energy is 0, this kinetic energy is 0, this potential energy is 0. Yes or no? And there is no any work transfer also. So work transfer is also 0. Clear? Now, my dear, other thing is that there is no any initial mass in the tank. Why? Because the initial mass is evacuated. So there is no any initial mass. So M1 is also 0. So this is also 0. This is also 0. M1 is also 0. So what the equation left? The equation, it is in the form of Q heat transfer plus M inlet into H inlet is equal to mass, final mass of the system into U2. Okay? Plus, there is no any exit. Why? Because this is charging, not discharging. Only inlet is there. There is no any exit. So exit condition are 0. That means this is also 0. Very important. There is no any exit. This is also 0. So what is the equation now converted? Q is equal to MIHI M2 U2. All these are 0. So this is your conservation of energy. This is your conservation of energy for this problem. That's it. Now, here beta, in this question, what is given? In this approach, what is given beta? If you apply, so in this, once you have to, this Q it is given. Enthalpy, their ideal gas, for the ideal gas, very important, for ideal gas which behave as a perfect gas, what is that? H is equal to CPT and U equal to CVT. This you know. So CP and CB is given, T it is given. Now mass we have to find. What is the mass? So apply conservation of mass principle. So for the steady or unsteady problem, we have to apply the two conservation. First mass conservation, another is energy conservation. So due to the energy conservation, we have this equation. Now we have to apply the conservation of mass. Conservation of mass. What is the conservation of mass, beta? Mass at inlet is minus mass at exit is equal to change in mass of a system. This is for the system. Yes or not? So, beta, there is no any exit is there. Why? Because this is not discharging, this is a charging. So, exit is 0. Exit is 0, and now M2 minus M1 is there. Now, initially evacuated, so M1 it is 0. Initially it is evacuated, so M1 is 0. So, what is the conservation of mass principle? That means mass at, what is the inlet? Is the same mass of the system at final. So, Mi is equal to M2. That is the very simple. Mi is equal to M2. Put here, so what is the equation we have? That means we have Q equal to Q plus MIHI mass inlet, enthalpy at inlet is equal to mass of the system final, energy of the system final. Now, my dear, here this Q is equal to mass M2, matlab, so Mi is equal to M2. So, put here M2 HI M2 U2. Okay. So, this Q is equal to Q plus M2. What is HI? CP TI is equal to M2. What is U2? CV T2. Clear na? Clear? CV T2. Now, CP and CV given. We have to find the T2 temperature. Initial inlet temperature it is given. CP given. Now, M2. How to find M2, beta? To find M2. To find M2. How to find M2? To finding the M2, since gas is an ideal gas, we have to apply the state equation, ideal gas state equation. What is that? P2 V2 is equal to M2R T2. We have to apply. From this equation, what is M2? M2 is P2 V2 by R T2. We have P2. P2 is what? Pi. V2 you have R T2. So, Pi we have, V2 we have, R we have. So, it is in the form of T2. So, put mass M2 instead of T2. So, if you take like that, Q is equal to M2, you have to take common. So, CV T2 minus CP TI. Okay. So, what is M2 here? M2 is Pi V2 R T2 CV T2 minus CP TI. Now, my dear, what is given here? Here P2 is equal to Pi. So, Pi it is given. How much it is given? 600 kilopascal. V2 it is given 8 meter cube. Heat loss Q1 to 2 it is given minus 1000. Okay. CP, CV given. CP and CV also given. Okay. Ti it is given. Inlet temperature it is given with how much it is? 306 Kelvin. Put it in Kelvin. Put all this value here. That means instead of Q, you put minus 1000. Pi put 600 kilopascal. V2 put 8 meter cube. R 0.287. T2 we have to find it, CV put, CP put, TI put 30. From this equation, if you put the T2 is equal to, it is your 395.388 Kelvin. That's it. This is your answer. This is your answer. Clear? This is your answer. Okay. So what is that in this question? What is the motivation? Apply the conservation of mass. That means simply two equations. First, conservation of mass. What is the conservation of mass? Mass inlet, mass exit, M2 minus M1 of a system. That's it. This is your conservation of mass. Second one, conservation of energy. What is the conservation of energy? Heat transfer plus Mi. So mass in, through that H in internal Hi plus Vi square by 2 plus Gzi is equal to change in energy M2 U2 plus V2 square by 2 plus Gz2 minus M1 U1 plus V1 square by 2 plus Gz1. So this is your internal energy minus M exit enthalpy exit plus V exit square by 2 plus Gz exit plus W. That's it. This is very simple. This is very simple. Hi Nitin. Hi Nitin. Thank you. Thank you Nitin. This is very simple. Okay. So apply conservation of mass, apply conservation of energy. This conservation of energy is uniform flow unsteady state. Flow is uniform but state is unsteady. So for the unsteady state, the property of any property of the system with respect to time is not zero. That's why the time with respect to time, there is a filling, charging out, discharging of a time. Clear? Clear? Now, so this is the first question in 2022. This is the first question in 2022 which is related to the conservation of energy. Now we have to take, this is the first law. Now we have to take the next problem of the same year for the second law of thermodynamics. So my dear, I will give you a brief introduction. See, we have to find the heat transfer. Find the heat transfer. See, heat is a vector quantity. You know that? Heat is a vector quantity. So it's have a magnitude and have also a direction. So the magnitude of heat, that means amount of heat. Who gives the information of amount of heat? First law of thermodynamics. And the direction of heat, who gives the direction of heat? Second law of thermodynamics. So this is the question related to the second law of thermodynamics. Okay. What is that? Please read the question very carefully. This is also very simple problem, but good question. This type of question is very basics. That means when you have to start the thermodynamics, this type of question must you have to have knowledge about that your concept, that will build your concept. So in 2022, very basics and very good question is also there. That means one question is for the first law, second question is for the second law. So what is that beta? Second law gives the direction and first law gives the quantity. See, quantity and quality. Quality gives quantity, have a quantity, that means energy have a quantity, and that quantity have a direction if there is a heat and work. So the direction provided by the help of second law through the concept of entropy. So what is that, beta? See this question. What is they say that in this question? Please tell me. This question says that a steady state, see, this is your steady state. That means the rate of change of property within the control volume with respect to time is 0. The steady state, this is the mass flow rate 500 kg per second of steam enters the turbine. So there is a turbine control volume. So this is the control volume, steady control volume system. In 99% in the engineering application, the device which is used for the open system that follow the steady condition. So turbine is also a case of the steady condition. So steam enters with the specific enthalpy, that means enter its enthalpy equal to 3500 kg per kilojoule per kg, and entering with mass will enter. So along the mass the properties also enter. So from the mass, if mass will enter, that mass have a property, that means enthalpy 3500 and its entropy 6.5 kg. What is the function of turbine? Turbine will expand, that means the pressure will reduce. So it expand, whose expand? Turbine expands the fluid reversibly. What is the mean by reversibly? Very important. That means there is no any generation. If you apply the entropy balance, there must be a generation of the energy entropy, but for the reversible case the generation is 0. So for the reversible in the turbine to the condenser pressure, that means it will reduce, turbine will reduce from the boiler pressure to the condenser pressure. So condenser pressure, during that heat loss from the turbine at a temperature 500 Kelvin. So the turbine have an open system that have a control surface. That control surface of a turbine have a temperature 500. Now, if the exit condition is there, why? Because open system have an inlet and exit. So exit condition have a given a specific enthalpy and a specific entropy it is given. See this one, if the pressure will expand, the enthalpy will reduce and also the entropy will reduce. Why? Because there is no any generation. If there is a generation, this entropy must be increased. But if there is no any generation, that means there is no any reversibility, during the expansion the entropy will reduce. Okay, so at the exit the entropy will reduce respectively. So turbine is a work output device. So what is the work output from the turbine in megawatt? Okay, in megawatt. Okay, my dear. So let's start this one in megawatt. Okay, so this is your turbine. If you look at that, this is your steam turbine. This is your steam turbine, and this turbine is a steady device. That means what is the change within this system? So this is our system. This is our system, and that system is our control volume. So this is our control volume is there. So this control volume, there is at inlet I and there is exit E. During inlet and exit there must be a work will produce W. W work will produce. During that there must be a heat loss from the system. Clear? Heat loss, that means this is a negative sense. Now my dear, see this one. So this is your I, not one. This is I and this is your exit. And during the inlet and exit, the system will change 1 to 2, a steady manner. Okay. So there is an inlet and there is an exit. During the entry and exit, the system property will change. But that property change is independent with time, so that the steam turbine is a steady device. Okay. So expansion in the turbine, that means expansion in the turbine is a reversible manner. if it is a reversible manner, in the question it is given it is in reversible manner. So if it is in reversible manner, entropy generation, and this entropy generation, it is a path function, very important, is 0. That is the first line. That is the first line. Now we have to write the equation of entropy balance. My dear, in a thermodynamics, there are 4 equations: mass balance, energy balance, entropy balance, and exergy balance. Very important. In the basics thermodynamics, in BTech level, you have a mass balance, you have an energy balance, you have an entropy balance, and you have an exergy balance. This is your thermodynamics. In the case of fluid mechanics, there are 3 balance: mass balance, momentum balance, and energy balance. Clear, beta? So this is the entropy balance. What is the entropy balance? Entropy in minus entropy exit plus entropy generation is equal to change in entropy of the system, S2 minus S1. If you write rate basis, so ds by dt of a control volume. So this generation is a very important thing, beta. This generation, okay, this is the entropy generation. Entropy generation, and this entropy generation is a path function, not a property. Path function. It is not a property, beta, of the system. Entropy generation is not a property of the system. It is the path function. That means this entropy generation is 0 when there is a reversible process. Okay, so the system is reversible within the system, so entropy generation 0. So this entropy generation, it is 0. Why? Because this is your reversible process. So and this is also 0. This is also 0. Why? Why this is 0? Why? Because steady state. Steady device. Steady device. This is also 0 for the steady device. Now, my dear, what is that then? So, what is the equation? Rate of entropy at inlet minus rate of entropy at exit is equal to 0. This is the entropy balance. Now, my dear, very important, that this is your entropy transfer. This is your entropy transfer. Mind it. This is your entropy transfer. Very important thing is there. This is your entropy transfer. This is your entropy transfer. And beta, entropy transfer is due to following factor: mass. This is due to mass and heat. Very important, not work. Not work. That means due to the work transfer, there is no any entropy transfer. The mechanism of entropy transfer is due to mass and heat only. But the mechanism of energy transfer is by the mass, heat, and work both. All three are responsible to transfer the energy. But entropy transfer only 2 things: mass and heat. Okay? So what is the entropy at inlet? The same entropy at the exit. That is the entropy balance in this case. Okay. So we have to write this equation in this case. What is that, beta? Entropy balance So what is that? Rate of entropy at inlet is equal to rate of entropy at exit. So my dear, someone asks you, for the open system, if the rate of entropy at inlet is equal to rate of entropy at exit, at what assumptions? What is the different assumptions? So assumption, what is the assumption? Assumption number first, steady device and reversible process. And reversible process. Under these two conditions, what is the entropy at inlet to the turbine is the same as the exit of the turbine. Now my dear, this is the entropy transfer, and this entropy transfer is responsible for two factors. One is the mass and other is the heat. So entropy in, so this is your turbine, and in the turbine there is in is there I, and there is exit is there E. So this in is mass rate in, and there is a mass rate exit. So due to the mass in, there must be an enthalpy, and there must be a enthalpy. Due to the mass exit, there must be a enthalpy exit. During that, there must be a heat transfer. 1 to 2. Heat transfer. And this heat transfer is for the system boundary. So how to write entropy in? So entropy in is due to mass, that means mass flow rate at in. So write specific entropy at inlet. So this is your in, okay, this is your in. What is the exit? Mass, due to the mass at exit, entropy, specific entropy at exit, and there must be a heat exit. So Q1 to 2 entropy exit due to the heat transfer divided by T, and this T is the system temperature, system boundary temperature, across which this heat will transfer. System boundary temperature across which, that means if this is your system boundary, let's suppose this is your temperature T, and in this one there is a heat transfer, in this one there is a heat transfer. So what is the entropy? Q by this T. This is your entropy transfer due to the heat. So this entropy in is only due to the mass, but entropy exit is due to the two factors. One is the mass and other is the heat. So what is the entropy in is equal to entropy exit. So this is your entropy in SI, and SI is only due to the mass. This is your entropy, rate of entropy in, and this is your rate of entropy exit, S of exit. So exit, it is your heat and mass both. Okay, put this all value, put all this value. So what is the mass at inlet? 500. What is the entropy at inlet? 6.5. What is the mass at exit? 500. What is the entropy at exit? 6.3 plus what is the heat transfer? Heat out is divided by what is the temperature, system temperature? 500. Now my dear, from here you can easily find what is the heat out from the system in megawatt. That means this is rate basis. This is rate basis. Megawatt, that means what? Joule per megawatt. That means watt is what? Joule per second. That means rate basis. So from here, the rate of energy out, this is equal to how much? We have an answer. This is your 5,550 50,000 kilowatt. So beta, this is the rate of heat out. Now what they are asking, but they are not asking what is the rate of heat out. They are asking what is the work transfer. What is the work transfer? So heat transfer, for the heat transfer, we apply the second law of thermodynamics. We apply the second law of thermodynamics. We apply the second law of thermodynamics. And for the work transfer, we apply the first law of thermodynamics. Very simple. We apply the first law of thermodynamics. What is the first law of thermodynamics? For the open system. So this is for the second law of thermodynamics. This is your second law of thermodynamics. So from the second law of thermodynamics, entropy balance, you have to find the heat transfer. Now you have to find the work transfer, apply the first law of thermodynamics. So first law for open system. Open system. And my dear, this open system, it is your steady device. Steady device. So we know that for the steady state energy in equation, what is that? What is the amount? That means heat transfer is equal to mass at inlet Hi plus Vi square by 2 plus Gzi. There is no any change in energy of the system is equal to mass flow rate exit He plus Ve square by 2 plus Gze plus W. What is the difference between this equation and this equation, beta? What is the difference between this equation and that equation? In this equation, there must be an energy change of the system. Why? Because this is an unsteady state. But in this case, there is no energy change of the system. Why? Because it is a steady state. So here the system is stationary. So these terms are negligible. There is no any change in kinetic and potential energy. So these are the zero. Okay. And now what is that? That means a mass flow rate in is into enthalpy plus heat transfer is equal to mass flow rate at exit, enthalpy at exit plus work transfer. Generally, this is nothing, this is shaft work. What is called? Shaft work. Shaft work. That means work producing by the turbine. So we have mass at inlet. What is this value, beta? We have all this thing. What is that? Mass at inlet, mass flow rate at inlet, it is given 500 kg per second, and H at inlet, it is given 3500 kilojoule per kg, it is given. H at exit, it is given how much? 2500. It will reduce. Why? Because it is expansion. Okay, and this is steady state. So steady state, Mi is equal to M exit. Why? Because there is no any change in mass within the control volume. So what is the mass at inlet? The same mass at exit. Okay, put all this value. So this is your 500 into 3500 minus, this is your heat loss, so minus 5000, 50,000 is equal to mass exit you have 500, exit enthalpy you have 2500 plus work transfer. From here, you can easily find what is the work transfer, work developed. This is your 450 megawatt. So what is the beauty in this question? In this question, we have to apply the conservation of mass. we have to apply the conservation of energy and we have to apply the conservation of entropy balance. So in this question, what is the mass balance? Mass balance. What is the mass balance, beta? Mass, rate of mass in minus rate of mass exit is equal to dmCV by dt. What is the energy balance? Energy balance. What is the energy balance? What is the energy balance? Rate of heat plus mi hi plus vi square by 2 plus gzi is equal to m dot exit h exit plus v exit square by 2 plus gz exit plus w. Okay. Third one, what is the entropy balance? What is the entropy balance, beta? Third, entropy balance. Entropy balance. What is the entropy balance? What is the entropy balance? Rate of entropy in minus rate of entropy exit is plus rate of entropy generation is equal to ds by dt of a control volume. My dear, this is 0. Why? Because steady device rate of entropy, this is 0. Why? Because steady device, and the generation it is 0. Why? Because reversible. Clear? So in this equation we have to apply this all three equations. This is the beauty of this question. This is a very straightforward question, and this question is always tried to solve while you have to practicing the questions of a thermodynamics. While you are practicing the question of a thermodynamics, you have to try to solve a such problem in which that these all three equations are applied. That problem is a very basics and good problem, and also there is a most expected question of the GATE. Clear? This is clear? Everyone please, this is clear, beta? Everyone please, this is clear? This is clear, beta? Okay. So now we have to take the next problem. This is the next problem. This is the problem related to the power plant. What is the question? Please read this question, beta. What is the question? Please read this question. So this is the question related to the steam power plant. Okay. Steam power plant works on a Rankine cycle. Gas power plant works on a Breton cycle. Clear? Clear? So steam, see, this is a Rankine cycle, okay, based on a Rankine cycle. Steam is initially expended in a high pressure turbine. So in the steam power plant there is a more than one turbine. One is the high pressure turbine. The steam is then reheated, very important, reheated in a reheater. That means after the expansion of the steam from the first turbine is called high pressure turbine. That means after expansion of the steam from the high pressure turbine, it again reheated. Where it is reheated? So reheater. Okay. So reheater, it is heated and then it is finally expanded. Very important. Then it is finally expanded to a low pressure turbine. So there are two turbine, high pressure turbine and low pressure. So expand in a low pressure turbine. The expansion work in the high pressure turbine, it is given. How much it will work will develop by the high pressure turbine. And the low pressure turbine will develop this work. Whereas the pump work, that means what is the function of pump? To pump the fluid from the condenser pressure to the boiler pressure. In that one, the work will consumed 15 kilojoule per kg. The cycle of that means this Rankine cycle, which is based on the reheated, that have a efficiency 32%. So they are asking that the heat rejection in the condenser. So there must be a two pressure in the Rankine cycle. One is the boiler pressure, other is the condenser pressure. So in the boiler we have to supply the heat, and in the condenser we have to reject the heat. So how much heat will reject from this reheater cycle? Now my dear, so this is your reheat. This is your reheat. Okay, my dear, this is your high pressure turbine. This is very important diagram is there. Please focus here. There are two turbines. These are coupled with the same shaft. One is the high pressure turbine, other is the low pressure turbine. Okay. High pressure and high temperature fluids enters into a high pressure turbine, and that high pressure turbine developed a work. In this question it is given. This is W, let's suppose high pressure turbine, it is given. Now this steam, it is not going to the condenser directly. It will come out and go to the reheater in the boiler. Again it is heating. Again it is heating. And it will return to go into the low pressure turbine. From where again there is a work output. So this is a work output from the low pressure turbine. Now, after that it will expand and go to the condenser. From that condenser there must be a heat will reject. And then there is a pump. In this pump, it is given that work input to the pump. So what amount of this condenser will reject the heat? The question is asking in that like manner. What is that, beta? If you draw the TS diagram, you can observe very carefully. Someone asks you, what is the purpose of reheating? Why we are done the activity of reheating in the Rankine cycle? The prime motive is, the prime objective of reheating to improve the quality at the exit of the turbine. Okay, let's suppose there is 1 to 2, it is a boiling process, there is a boiler, there is a pump is there. So 1 to 2, this you have to pump. Okay, now from 2 to 3, there is a heat addition. 2 to 3, there is a heat addition in the boiler. Now from 3 to 4, there is a high pressure turbine expansion. 3 to 4, so this is 3 and this is 4. This is a turbine, high pressure turbine expansion will take place. Now my dear, this 4 to 5 is a reheater. This 4 to 5 is a reheater. See, this is your 4 to 5 is a reheater, and due to this reheater, the steam temperature again will increase. This increment will be equal to this, that means the temperature of T5 may be equal to T3, may be less than T3. It will depend upon the how much the extent of the level will be increasing. Now it again expand to the low pressure turbine. Again expand to the low pressure turbine. Now after that it will condense. So from here it will reject. Now my dear, if you are not doing the activity of reheater, the expansion will light takes place. Yes or not? If you are not doing this reheating, the expansion is directly come here. That means 3 to this is 6 dash. Let's suppose expansion will directly come here. So while you have to reheating, the 6 dash point will shifted at 6. So the quality of the steam will improve. When the quality of the steam will improve, so the expansion, see previously the turbine will handle this much of the wet steam, but now the handling of the turbine of the wet steam is reduced. So the life of the turbine will improve. See this one, initially if you not reheating, their part of the expansion will take place in the wet region, yes or not? The part of the expansion will take place in the more part of the expansion will take place in the wet region. But while you have to reheating, very less part of the expansion in the wet steam. So the water content particle in the turbine will be less. So the blade, life of the blade will improve. That is the purpose. So what is the purpose? To improve the quality of the steam. Quality of the to improve the quality of the steam. It will improve. That means increase the dryness fraction. Increase the dryness fraction. Dryness fraction will increase. This is the prime motive. That means this is a main objective. Main objective. What is the main objective to reheater? Reheating to increase the dryness fraction. Okay. So we have to find the what is the heat rejection. What is the heat rejection? So from that one we have to find the heat rejection. My dear, if this is your cycle steam, so what is the efficiency? So this is like that. Yes or not? This is like that, beta. This is like that. Okay. Now my dear, this is your TS diagram. Okay. T and S entropy, temperature and entropy diagram. This is what saturated vapor curve. This is saturation curve, not a vapor curve. This is saturation curve. Saturation curve. There is a one boiler pressure. There is one minimum pressure is the condenser pressure. Okay. So this is point number 1, inlet to the pump, and this will exit from the pump at point 2. Now 2 to 3 there is a boiler, and let's suppose this is your exit from the boiler and entry to the high pressure turbine. So at here there is a expansion will takes place. Expansion will takes place in a high pressure. Again it is reheating, and again it is expansion will takes. Let's suppose this is there. Expansion will takes place. Let's suppose this is there. It is like that, no problem. Let's suppose it is like that. You have to make a scale, proper scale. Let's suppose this is entry. Okay, you have to change the color so that it is very good visible. Okay, this is your entry 1. Let's suppose the 2, and this is 3 entry. From here there is a expansion will takes place. 4. Again reheating will takes place. Again there is expansion. So this is 4, 5, 6, 7, and this is 1. Now my dear, this 5 point may be at the saturated point. It is not like that. It is not like that, beta, ki sir, this 4 point is always here. No, it is not like that. 4 point may be at the saturated vapor curve, no problem. 4 point may be saturated vapor curve, okay. So this 4 point, like this 5.3, this 4, this 4 point, this is your 5 point, and this is 6 state. So this 4 point may be saturated. You have to draw like that, anything, okay. Now my dear, here heat supply in the boiler, here heat will reject in the condenser. In this one, there is a work out from the high pressure turbine. This is work out in the low pressure turbine. This is a pump work input. So my dear, what is the efficiency of the cycle? What is the efficiency of cycle? Net output by heat supply, yes or not? Net output by heat supply, you know that. Now what is the first law from the first cycle? This is for the cycle. So for the cycle, what is the net work transfer? Net work for the cycle, what do we know that? For the cycle, yeah, you can say that. For the cycle, net heat transfer is equal to net work transfer, you know that. So W net. So what is that? Heat in minus heat out divided by heat out. Heat in. So this is your 1 minus Q out by Q in. Yes or not? Q out by Q in. Now the efficiency it is given. Now W net it is given, beta. What is the W net? Total net work out W high pressure turbine plus W low pressure turbine plus minus pump, it is minus, why? Because work in W by the pump, okay. So if you put this one, what is the efficiency it is given? 0.32. What is the W net? Put this value 400. In this one there is a 850. Pump work it is given 15 divided by heat in. Yes or not? So what is the heat in here? How much the heat will supply? So heat in it is your 3859.37 kilojoule per kg. This is your heat in to the system. This is your heat into the system. Now we have to find the heat out. So one, you have to find a heat in from this equation. 1 minus heat out minus heat in. So you have heat in, you have efficiency, find heat out. If you find heat out, this is approximately 2624.37 kilojoule per kg. That's it. Clear? Clear, beta? So this session is approximately 1 hour session. So some question also left, but we have to try to solve in the next session. Please, what is the motive of this question, beta? The motivation of this series is to improve your concept. And once you have to finish the subject of a thermodynamics, whatever you have to study, at where you have to study, no problem. But once you have to finish the thermodynamics problem, please try to solve, and you have to also check whether the concept what I have delivered in front of you, that is you have to grasp or not. If you have to very comfortable for that one, this is very good for that one. Try to solve. If you have any problem in any type of question, please comment on the YouTube comment box so that we will be resolved to your question. Okay? Stay tuned. Thank you. Bye-bye.